Hello, I'm Pepijn de Vos. Welcome to my presentation about Project Epicula, which is my internship project that got turned into a paper. I also want to thank Daniel and Michael, who were my supervisors and the ones who also helped me turn this into a proper paper for my internship report. I will be talking about how I documented the bitstream of Gowin FPGAs and what you can do with this. So to give an overview, first I will talk a bit about the background of FPGAs and open source tools. Then a bit what my internship was about synthesis and fuzzing and the results, and then what you can actually do with this research. So let's jump in. Maybe some of you know this already, but I'll go through it briefly. Basically, an FPGA is a programmable logic device where you take a hardware description language and then first go to a Boolean logic and then to lookup tables and data flip-flops. And I've sort of visualized this here where you, first you do the synthesis and then you get sort of like these, logic gates. And these logic gates get turned into a lookup table for the logic functions. And these get connected with lots and lots and lots of multiplexers. And as we'll see later, actually the most of the FPGAs is just multiplexers inside. So inside an FPGA are basically logic tiles. And in each logic tile are like a couple of flip-flops and lookup tables that do the logic. And then there's lots of routing, and this is shown smaller here than it actually is. And this routing connects the lookup tables to the wires, and there are wires that are going to like one tile next to it, and then 2 tiles next to it, and 4 tiles next to it, and 8 tiles next to it. And you can see in the slide how many of each there are. And on top of that, there are a few wires that are global across the whole FPGA, like for clock routing. So the process of taking your design and making it into a binary for an FPGA is roughly displayed here, where you start with like Verilog or FPT2020 or whatever you have, and then there's the commercial cool tools like Quartus, and there's this old academic project, and I will be mostly talking about Josys and ABC, which then spit out a netlist that you can place and route. And again, this can be done with commercial tools or open source, in this case NextPNR, which then produce another sort of netlist file with place and route information, which you can then feed to a bitstream assembly program that actually makes the binary for your FPGA. Project Epicula is basically my internship where I try to make a Josys and NextPNR and bitstream tools for Gowin FPGAs. So this includes sort of the synthesis part where you just take FPT2020 or whatever and turn it into a netlist, and then also integrate it into the place and route part and write tools to then turn this into a bitstream. So synthesis in Josys basically starts with hardware description language and a cell library that describes the primitives that the vendor provides. And this part is sort of described in the manual, so it's not too hard. So first you load the hardware description language in your cell library. And the first thing that happens is it sort of gets synthesized in coarse level cells, which are like, sort of high level blocks, which then gets lowered into fine like single wire, single logic cells, but still like abstract ones. And finally, the tech map step. It takes the abstract ones and converts it into vendor-specific technology nodes, and then it writes this netlist out. So the synthesis part is kind of in the manual, but the place and route part is not at all. So what you need to do to figure out how the internals of the FPGA work is you basically generate a bit stream with the official vendor tools, and then you modify one tiny bit of the bit stream and generate another one. And then if you compare the two bit streams, you will see that like one bit is flipped, for example. And then you do this for all the bits, and that's sort of the simplified view of how to fuzz an FPGA. Of course, like changing a single bit and then describing the meaning of this bit is where the hard part is. But yeah, fuzzing is the preferred method for documenting an FPGA bit stream, because you're not not digging too deep into the vendor tools. So for this project I wrote several, starting from really simple bash scripts that just ran the tools to more advanced Python program that tried to combine several different runs together. The roadblock in this particular FPGA was that the vendor tools do not allow you to specify any routing or constrain the routing or see the routing in the output. This makes it almost impossible to do any fuzzing on the routing, because you just get the random wires all over the place basically. So for the routing, I did actually look into decoding some files from the vendor that they were provided, because these vendor tools, they include binary data files that the tool knows how to parse and interpret that describe the FPGA. So if you just open these in like a hex editor or something and just stare at them long enough, you might be able to see their meaning and try to figure out what they are, and some other things that you can do to the binary files. But yeah, basically, the long story short, you try to reverse engineer the file structure and parse the file, and that you get data out of does not mean you know the meaning of this data. So then again, the hard part is once you have the data, getting meaning out of it. But yeah, eventually then you can generate this kind of picture where you see, oh, okay, this has all these different tile types, where you see around the edges there's the output buffers and the PLLs, and then in the center there's a block RAM and another row that's kind of special, which is the global clock spine, and then the blue ones are all the routing fabric, the configurable logic unit, function units call them. Yeah, configurable function units, they're called in Gowin language. And then you can do the same for the tile. So like each of these blocks has all these bits in them, and there's a file that describes all the bits. And here I gave each different description a different color, so you can sort of see which bit belongs to which. And you see at the bottom row there is 8 lookup tables and 6 data flip-flops. Like the one pair of LUTs doesn't have a data flip-flop, so there's 6 data flip-flops and 8 LUTs per tile. And then above it is all muxes. And in the text that's written in the mux, it is written which wire this mux is driven. So for example, N21 is a wire that goes north, that is 2 tiles long, and it's the first one, and there's like several of them, so there's like also 27, and yeah, all sorts of wires also for the LUT inputs and everything you can think of that you might want to connect. Yeah, and once you combine these things, once you understand this then you can start writing tools for it. And yeah, this is a RISC-V core that was synthesized using my open source tools. And because my tools are not so completely yet, it's not using all the resources that it would normally use. So also the RAM is just lookup tables at this moment. So it almost fails the whole FPGA, but it works. And this program basically has a RISC core that calculates primes. And I loaded then the bit stream back into the floor planner of the vendor so you can see what's going on. And here you see a picture of the program running basically. And yeah, it outputs like in binary the numbers, and well, if you have a calculator handy, you can verify that they're indeed prime. And that is it, almost. The first half of it. Because, yeah, okay, this exists now, but why does it matter? What can you do with it? Why is it important? So here I made a little overview of why it matters for research. And it depends on what you try to do in your research, for example. So if you want to make synthesis algorithm, for example, you would have to make some academic thing. And yeah, then you can say, okay, it was better than the old thing, but you can't really do it on like commercial FPGAs or use it in practice. Well, if you have these open source tools, you can take these advancements in your research and just apply them to real world uses, basically. And the same kind of thing is true for place and route research, because yeah, there was this Verilog routing thing, which is sort of has this imaginary FPGAs where you can try your algorithms. And only now Verilog routing is getting some support for real FPGAs. But yeah, Nextpreneur and Verilog routing allow you to now do this on real FPGAs and actually have an impact with your research on commercial FPGAs. And what I also think will be really exciting is in hardware description language research, because so far all these hardware description languages, the fancy high-level ones, they have to compile down to Verilog basically usually, because that's what the vendor tools support. And now that if there's open source tools that support all your FPGAs, you can just write a new synthesis frontend for the open source tool and target some well-defined intermediate language. And yeah, then I hope to see very much interesting innovation in this space because of that. Another thing that I think can be a huge advantage is education. Sipit released recently this $5 FPGA board, which is pretty amazing. When I did FPGA courses in university, you have to like write a paper, and then your group gets assigned one FPGA and you have to give it back, and yeah, it's a fight over who gets to use it. And with this kind of board, you can just give every student an FPGA or tell them to get it from the store or whatever. It's super cheap, so very easy to get started. Only problem with the current tools is, yeah, you need the license, and I've heard from several people this is a big obstacle in using it in several contexts. They're not super fast in replying sometimes. Well, with the open source tools, you don't have this problem. You can just install Go, €5, and you're on your way. So yeah, you get cheap FPGA boards, no licenses, and it works actually on all operating systems, all major ones that I'm aware of. Well, usually Linux in the EDA space means Red Hat Enterprise Linux and not whatever you're using. What's also interesting is that this Yosis is kind of gearing towards high synthesis speed, which is nice because you can just iterate quickly. And they're like not horrible, because like basically this internship was motivated largely by my frustration with Quartus, so there's that. And also there's lots of cool stuff going on in the open source world, like formal verification with these open source tools, which is really interesting. And yeah, I want to thank all the people who supported this project financially, mainly Symbiotic, where I did my internship, and all these other people who sponsor me on GitHub sponsors and Patreon. And also thank you for listening, and I think there will be a Q&A later.